In this video, we will discuss about the third type of integer programming, still in decision-making analysis subject. Let's see. Okay. Yeah. So the third type of integer programming called as modeling or in 0-1, modeling with 0-1 or binary variables. Yeah. We can demonstrate how 0 and 1 variable can be used. So typically in this type, the result will be in the number of 0 or 1. So the result must be in binary variable. Binary variable means 0 and 1. 0 and 1. 0 means if a certain condition is not met, and 1 if the condition is met. Binary usually used by computer program as a digital. So the value of binary only, it's called binary only 2, 0 or 1. This is a case if there is a project, a common capital budgeting problem. Usually 0-1 is related with budgeting problem, because one company cannot funding all the project. They must choose which project that will be funded and which project will not be funded by the company. That's why we need to solve it or to find the result in binary, in 0 or 1. 0 means the project will not be funded by the company, and 1 means that the project will be funded by the company. That's the example of the case. So in this case, we can see the details in this case. This case is about QM chemical company. This company considering 3 possible improvement projects. The first one, this company want to create a new catalytic converter. The second one is new software program, and the third one is expanding the storage of its warehouse. And this is clearly stated that this company cannot do them all because the budgeting problem. They want to maximize net present value of project undertaken and see the result, which project that will be funded. Maximum net present, so like the previous objective, there are 2 kinds of objective, maximization or minimization. In this case, because it's stated that they want to maximize net present value, so the objective is maximization. Maximization of net present value, but still considering the constraint, especially about budgeting, to find out which project will be funded and which project will not be funded. Let's see the detail. So there are 3 projects. The first one is catalytic converter, second one is software, and the third one is warehouse expansion, with the net present value details for each project. And there is a constraint, which is available funds. Available funds in year 1 is $20,000, and in year 2 is $16,000. This is how you read the table. The project concerned to the first project, catalytic converter. If this project will be funded by the company, then the company will get net present value as $25,000. To build or to implement implement this project catalytic converter, in year 1, the company have to pay $8,000, and in year 2, this company will need, or this company is going to pay for $7,000. For software, the NPV is 18,000, but it need funding in year 1 as $6,000, and in year 2 is $4,000. Actually, we can easily find the combination of the project that will be funded depend on the maximum NPV, but this project that funded must be still in budgeting number, or in the availability of budgeting costs. So in year 1, the combination must be under or equals to 20,000 of the available fund for year 1, and year 2 must be lower or equals to $16,000. Okay. Total funds used in year 1 is less than or equals to 20,000, and year 2 is equals to or less than $16,000. The decision variable for X1, or the result, 1 means catalytic converter project is funded, 0 otherwise. Otherwise means catalytic converter project is suspended or is not going to be funded. X2, if the result is 1, means software project is funded, 0 otherwise. X3, if 1, then warehouse expansion project is funded. If we see actually the case, this is the case. Actually, we can combine to find the maximum NPV. The maximum NPV can be derived from these two projects, catalytic converter and warehouse expansion. If the combination still in the budget consideration, then these two projects must be funded. 25 plus 32 NPV, the NPV must be in the highest number of NPV, or the optimum or maximum number. The 25 plus 32 means 57,000, and for the year 1, 8,000 plus 12,000, yeah, still in or exactly 20,000, still covered by the available funds for year 1, and for year 2, 7,000 plus 8,000 equals to 15,000, still lower than the available fund. So the result must be 101. That's the prediction. Actually, the result before we use QM or we use a manual calculation, sometimes we can just see and predict what is the result. So yeah, that's my prediction. I'm sure that your prediction just the same with my prediction. So the result must be 101. Now, before we put the case to be solved in QM or using QM application software, then we need to create a mathematical statement. The objective is maximizing NPV, net present value, X1 for catalytic converter, X2 for software, X3 for warehouse. So 25,000 X1 plus 18,000 X2 plus 32,000 X3. This is the net present value. Let's see if I write it manually. Then we will derive the objective to maximizing NPV. Oh, it's so bad. Max NPV, net present value, equals to 25,000 X1 plus 18,000 X2 plus 32,000 X3. Yeah. This is the maximum objective. And then for the constraint, there are two constraints which is available fund in year 1 and year 2. So the constraint, the first constraint, first constraint is in year 1 equals to, here you go, 8,000 X1 plus 6,000 X2 plus 12,000 X3 must be less than or equals to 20,000. And in year 2, 6,000 X1 plus 4,000 X2 plus 8,000 X3 must be less than or equals to 16,000. Yeah, 16,000. This is the 16,000. Yeah, this is the equation. We can move it. Yeah, here we go. It's the same with this one. X1, X2, and X3 must be 0 or 1. This is just the same. Just practice it. So you can see the equation or create the equation clearly. Then open the QM. The module is still the same, integer, new. We have how many constraints? 2 constraints, year 1 and year 2. Number of variable is 3. Catalytic converter, software and warehouse expansion. Okay, here you go. Sorry. X1, X2, X3. Constraint year 1 and year 2. Yes, just that year 1. X1 is catalytic. The maximax or the objective is 20,000, 25,000, 18,000, and 32,000. Year 1, 8,000, 6,000, and 12,000 must be less than or equals to 20,000. For year 2 constraint, 7,000 X1 plus 4,000 X2 plus 8,000 X3 must be less than or equals to $16,000. And all the variables are in 0, 1. Oh, wow, where is that? All the variable is in 0, 1. Just 0, 1 and 0, 1. Then solve it. Here you go. Our prediction absolutely right. So x1 is 1, x2 0, x3 1. So the two projects that are going to be funded by the company is X1, catalytic converter, and warehouse expansion, which will give the highest result of optimum net present value as $57,000. We can also see this equation, and this one is maybe the easiest one. Solution 1 for X1 or catalytic converter, 0 for hardware, and warehouse expansion is 1. The optimal profit is $57,000. Yeah, that's the answer. It's simple, right? Okay, so that's the third type of integer, which is binary integer, or we also call it 0-1 integer. You can do more practice with the other case in the slide or another sources. So that's all for integer. We already discussed 3 types of integer. So see you and stay safe for all of you.